Section 2.7 is where we talk about the periodic table in chemistry. While this isn't an actual periodic table from chemistry, this is one from an online game called Minecraft. The table of elements is something you're going to find that you're going to be using a lot of throughout the rest of the semester. So we want to get you acquainted with the different parts of it and how we can use it, as well as kind of where it came about. The main idea here in the arrangement of the table comes from the periodic law. And that law states that when you take all the elements that we know about and you line them up according from smallest mass up to higher and higher and higher masses, what we get is every so often we see this repeating trend of properties. So for 1, 2, helium has certain properties. We get over to neon, very similar to helium. Argon, very similar to helium and neon. And these seem to be happening at a certain interval. Again, lithium has a certain set of properties. And right after neon, just like right after helium, sodium has a certain set of properties that are like lithium. And then again, right after argon, just like right after neon, potassium has a certain set of properties that are very similar to sodium and lithium. So we get these repeating periodic property groupings when we arrange them from smallest to largest. So what we can do is just arrange them in a table and then put them so that we repeat or wrap around to the next row every time we get to the point where we start seeing a repeat in the properties of those particular elements. So here's kind of a really quick simplified version of the first 20 elements where it lines up nicely with the columns where things have very similar properties. Now keep in mind this is the periodic law, this isn't the theory, so the law is just summarizing the observation that when we arrange them in this way, they have similar properties. For the reasoning why, we have to wait until we get a little farther into the chapter and talk about electrons and where electrons are situated. So to get you kind of on the same page with what a periodic table is representing in terms of what sections have what kind of properties, things on the left side of this kind of diagonal line over here in the rightmost portion, so everything on the left of that line is a metal. Hydrogen is the one exception. You could really almost put hydrogen over here on the other side by group 17, but traditionally this is where we put it because it does also share properties with lithium, sodium, potassium, rubidium, cesium, and francium. But everything for the most part except hydrogen to the left of that line is a metal. So metals are ductile, meaning that you can hammer them and put dents in them and you can reshape them in that sort of way. They tend to melt at relatively lower temperatures. The other elements that form things like rock and quartz and things like that, those don't melt at nearly as low a temperature. The metals tend to be conductive. They conduct electricity. They can make a lot of them magnetic. They have ferromagnetic properties, meaning that they're similar to iron in some ways. So those things all have this kind of metallic type character. On the other side, you have the nonmetals. These are things that come out like powders or cakey substances or rock kind of looking things, or gases in a lot of instances as well. Some are liquids and some are gases. But these are referred to on the right side of that dividing line collectively as the nonmetals. In the middle, we have a couple of them that are right on the line. There's boron, silicon, germanium, arsenic, tin, tellurium, astatine. These are metalloids, so they have properties that are similar to metals in some ways and similar to nonmetals in others. So they're kind of at a transition point between the two types. Down here we have the lanthanides and the actinides, and these are actually metallic in character as well, although a lot of these are radioactive, so we're not going to be running into very many of those in the introductory chemistry lab. Another definition that we want to know is this idea of main group elements versus transition elements. And this is going to become even more important as we talk about the ions that form when these particular elements gain or lose electrons. And we can get a little bit more predictability in the main group elements for what ions form, and with the transition elements, not quite as well defined. So we have a little bit more of a hard time deciding what ions these guys in the middle will form. So we want to know which those are by name. Transition elements from 3 to 12. And they also have a whole series of names which kind of lend into their properties. The alkali metals, here in this kind of brownish orange, are very highly reactive. These are the ones that if you go up to YouTube and you say sodium and water, you get to see somebody throwing a chunk of a kind of buttery soft metal into some water, and boom, you get a nice big explosion because they're extremely reactive. The alkaline earth metals right next to them in this kind of yellowish color on this periodic table are still reactive, but they're not quite as reactive as the alkali metals are. As we kind of skip over all these transition metals, which have very similar properties to each other, and we go over to the other side, we have something that depends on what periodic table you're looking at, but a lot of periodic tables just list these in this section as the other metals or post-transition metals. And they have similar properties to each other. We already talked about the metalloids, and that these are some non-metals, sometimes called the chalcogens. And then here we have the, I don't know what you call this, teal, something like that. You know, it's kind of sea foam green or whatever that is. I'm not all the greatest with colors, but you have this column, which represents the halogens. So if you're thinking of halogens, you usually think of halogen bulbs and that kind of thing. These can be extremely reactive as well. In fact, a lot of these you think of in terms of agents that can sanitize things because they react with microbes and they kill them. So iodine is used for that purpose. Chlorine and bleaching type agents are used for that purpose. But these are also highly reactive, similar to how the alkali metals are highly reactive. And we will see these have very similar properties as well. Now this last row in kind of a darker blue are the noble gases. And the noble gases have the property of, for 99.9% of what we're going to talk about, they will not react with anything. And that can be good or that can be bad. If you want them to do something and change, then that's a bad thing. If you want to have some sort of atmosphere that's not going to burn, that's not going to react with whatever it is that you have in your cylinder or in your vessel, then these things are a great inert atmosphere to be able to use. They're all gases and very non-reactive. Now the elements down here are typically all radioactive. A good portion of them are man-made elements, meaning these are things that we've created by smashing atoms together and causing them to form heavier atoms. And so these man-made species are usually extremely short-lived, meaning that we won't really expect to actually run into any of these in normal day-to-day chemistry. Uranium and things like that you can sometimes bump into, and especially with nuclear reactors or nuclear weaponry type considerations. But for the most part, we're not going to have to deal with the lanthanides, named after this row that starts with lanthanum, or the actinides, which is this row that starts with actinium. So the first thing that we want to start taking a pass at here in terms of predicting that you're going to use a lot of is this idea of what the common ions that form are for different sections of the periodic table. And we're going to get more into why these are the ions that form later, but for now you just have to kind of memorize these things. In group 1 on the periodic table, right all the way down this column, these elements all form +1 ions when they form ions. In group 2, everything on this column is going to form +2 ions. For group 3, which is actually group 13 if we count across from the left to the right, which is the more modern system, I know your book uses 3A, 4A, etc., but most modern periodic tables actually have a list all the way across, starting from 1, going through the transition metals as 3 through 12, and then 13, 14, 15, 16, etc. But in group 13, most of these will have +3 charges. The things that you get down here start to be more like transition metals, where it's harder to predict the charge, but in general you can count on aluminum at least being +3. In this row, what you usually end up with is +4, and sometimes you get -4 as you go down this particular column in group 14, but we'll talk more about that later. As we get to this side, we've transitioned into the negative ions, the anions, right? Those are the negative ones, cations being the positive ones, and things in group 15 tend to be -3 charged. Things in group 16 tend to have a -2 charge. Group 17, -1 charge, and the noble gases are almost always neutral. And that's the main things that we want you to know, at least for now, about the periodic table.